afternoon, everybody. Today, I'd like to show you our results on co-sputtering of monocrystalline germanium tin for infrared photo detection. As many of you probably know, adding tin to germanium decreases the gamma valley energy. And for enough tin, we can switch from indirect bandgap of germanium to direct bandgap. So in general, adding tin allows to shift the direct bandgap more towards the infrared. And this is of interest because we can enhance strongly the absorption of germanium of this alloy at 1.55 micrometers, which is a wavelength of interest for telecommunications. In particular, ideally germanium tin, because it can be grown monolithically on silicon, it can be much cheaper compared to the commercial indium gallium arsenide technology, which is nowadays the most performant material. However, germanium tin at the moment is still does not perform as well as indium gallium arsenide. And there are two challenges for germanium, two main challenges regarding germanium tin. The first is that tin is only soluble up to 1% in germanium, which means that for process temperatures that are too high, we will get tin segregation out of the germanium matrix. And the second most important challenge is that the lattice mismatch of germanium tin on silicon is more than 4.2% and increases the more tin we put into the alloy. Lattice mismatch has to be relaxed through the formation of threading dislocations. And the threading dislocations are a source of dark currents, which are at the moment what limits the performance of germanium tin compared to indium gallium arsenide. We decided to use co-sputtering to deposit germanium tin because it's a cheap alternative it's a cheap technique for industrial applications. We can control individually two plasmas, a germanium and tin pure targets, and by varying the ratios of the power, we can tailor the composition of the germanium tin deposited film. We used pure argon or argon plus hydrogen as sputtering gases, and we started from a base pressure in the high 10 to the minus 8 or low 10 to the minus 7 millibars. I would like to start by showing you our results of on germanium substrates. So we were able to deposit monocrystalline germanium tin up to 9% of tin on germanium substrates of very high quality. We had an XRD rocking curve full width a maximum of 40 arcoseconds, which is comparable to the full width a maximum of the germanium substrate peak. And we had very low roughnesses of 0.5 nanometers. We also were able to get monocrystalline germanium tin on germanium, on silicon substrates. However, as expected, due to the lattice mismatch, we had a high degree of dislocation density in the order of 10 to the power 9 per centimeter squared. And this was reflected by the rocking curve full with a maximum of 1000 arcoseconds. The roughness was still acceptable in the order of 1.5 nanometers. If we look in the literature, we see that both experimental and theoretical values of absorption coefficients for germanium tin at 1.55 micrometers increase as the tin fraction is increased. So we performed ellipsometry measurements on germanium tin grown on germanium with increase in tin content. And we observed, so here we plot the effective index of complex index, imaginary part of the complex index of refraction, K, which determines the absorption coefficient in function of the photon energy. And if we zoom in around 1.55 micrometers, we indeed see that K increases as tin concentration is increased. However, we are not able to extract the absorption coefficient from these curves because we do not have the right dispersion model in our software. But still, we can clearly observe that the absorption increases. Now I would like to switch topic and talk about the dynamics of growth of germanium tin on the germanium substrates. If you look at the first stages of growth, we see that we have a 3D type of growth, which results in crystallites. And this type of growth is called Stransky-Krastanov, and it's due to the high lattice mismatch with the, not high, but it's due to the lattice mismatch with the germanium substrate. The crystallites are pretty high. As a matter of fact, we have a roughness of 3.44 nanometers, which is not so low. If we keep growing on this type of, with the same conditions, for much longer growth, we indeed get a flat film where the islands have coalesced, but the roughness is still pretty high, around 2 nanometers. So it is important to avoid this initial 3D growth in the first stages of growth because this can originate defects. So the first thing we tried was to decrease the temperature in order to favor 2D growth over 3D growth by decreasing the mobility of the atoms on surface. However, when we went from 275 degrees to 225, we did not observe a switch between 3D and 2D, but in fact, we observed at 225 a bunch of crystallites in an amorphous matrix, which we could determine thanks to Raman spectroscopy, which gave a crystalline germanium peak and an amorphous broad peak, a lower Raman shifts. On the other hand, for the sample deposited at 275 degrees, we only observed a clear germanium crystalline peak. So our approach to this problem was, instead of playing on the thermodynamics, we played on the kinetics. So we reduced the kinetic energy of the impinging atoms on surface by switching from DC source to an RF source. And the RF source allows to use a smaller acceleration voltage. In this case, we use 290 volts instead of 430. And this meant that we had the atoms impinging on surface had lower kinetic energy, and therefore they had a lower diffusion length, which resulted in a 2D growth instead of island growth. So we kinetically limited the Stransky-Krastanov growth. And indeed, and as a matter of fact, for this RF growth, we only had 0.35 nanometers of roughness, confirming the 2D layer quality, the 2D growth. If we look at the time series of this type of growth with the RF source, we see that after 20 seconds, we indeed still have islands. However, the roughness is only 0.5 nanometers compared to the 3.44 that we see here. And if you look at the islands, we can see that there's a lot of parts where the islands connect. So it means that the islands have already started to coalesce after 20 seconds. And indeed, after 2 minutes, we see a flat film. And if we keep growing a thicker film, we still maintain the low roughness of 0.5 nanometers. So we try to do the same thing on silicon. However, if we compare these two growths of the same film on germanium and on silicon, we see that while on germanium we have this connection between islands, on silicon, after 20 seconds, we still do not have any island that looks connected. And this is also reflected in the roughness, the higher roughness, meaning that we have higher islands. And if you look at the time series of this sample, of this film grown on silicon, we see that after 3 minutes, we start having coalescence, but we still have holes, and the film roughness increases. And after 30 minutes, we get full coalescence of the islands, but we have a high roughness of 2.4 nanometers, which is due to the fact we have this late coalescence of the islands. What is most concerning, though, is that the late coalescence of the islands causes defects at the interface. If you look at this image of high angle annular dark field stem, we see that we have defects at the interface between silicon and germanium tin. And if we do EDX, when we did EDX, we saw that we took a region far from the interface of germanium tin and then a region of a defect. And we observed that the spectra were exactly the same, meaning that the elements in the two regions are the same, but the spectrum in the defect had much lower intensity, meaning that there's less material emitting X-rays. For this reason, we believe these are voids that are created because of the late coalescence of the islands, and they are not completely filled of material. Moreover, looking at TM imaging, we saw that these voids looked like they were a source of nucleation of stacking faults, which of course worsened the crystal quality. So it is important to switch to 2D growth also on silicon. And for this, it is probably necessary to use a germanium buffer, like it's reported in literature, like it's often used in literature. Finally, I'd like to show that when we measure, we were able to measure the absorption coefficient for a germanium tin film on silicon by using an anti-reflection coating. And for a germanium tin with 5% of tin, we got an absorption coefficient at 1.55 of 9,500, which is already higher than the absorption coefficient of indium gallium arsenide, showing that we don't need much tin in our film to get better absorption than indium gallium arsenide. So I'd like to conclude by repeating the fact that co-sputtering is a cheap solution for epitaxial deposition of germanium tin, that indeed the high quality obtained on germanium shows the potential of this technique, although we still have a high dislocation density of silicon. And with co-sputtering, we showed that with co-sputtering, we can individually play with the kinetics and the thermodynamics of the system, where the kinetics are controlled by the acceleration voltage of the plasma and the thermodynamics by the substrate temperature. This is important because we need to kinetically limit the Stransky Krasnov growth in initial stages of deposition. And finally, in the future, we will perform some electrical measurements in order to fully assess the potential of this growth technique for device applications. I would like to conclude by thanking my lab mates from LMSC, Laboratory of Semiconductor Materials at EPFL, and a knowledge of funding agencies in Swiss. And thank you for listening, and I'm happy to answer any questions.